Picture a galaxy, millions of stars spinning together in a delicate cosmic dance. Now think about this. The stars on the outer edges of that galaxy aren't moving the way they should. They're going too fast. According to what we know about gravity, these stars should be flying off into space, but they're not. Something is holding them together. Something invisible. We call it dark matter. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with light at all. It's completely invisible to our telescopes. And yet, it's everywhere, woven to the fabric of the universe, shaping the cosmos in ways we can only begin to understand. Here's what we do know. Imagine you're weighing the universe. You tally up all the stars, planets, gas, and dust, the things we can see. But when you add it all together, it only accounts for about 5% of the universe's total mass and energy. 5%. So what about the rest? About 27% is dark matter, a mysterious, unseen force that shapes galaxies and clusters of galaxies. The remaining 68% is something even stranger, dark energy. But that's a story for another time. For now, let's stay with dark matter. We first began to notice its presence in the 1930s. Astronomer Fritz Zwicky was studying a cluster of galaxies, and he found something odd. The galaxies in the cluster were moving so fast that they should have torn apart. Yet they stayed together, as if bound by an invisible glue. Decades later, more evidence came to light. In the 1970s, Vera Rubin and Kent Ford observed spiral galaxies, and they saw the same pattern. The stars far from the center of the galaxies were moving too quickly. Gravity, as we understood it, couldn't explain their behavior. The only explanation was that something invisible, dark matter, was creating enough gravitational pull to hold everything together. But what is dark matter made of? This is where the mystery deepens. Scientists think it could be made of particles unlike anything we've ever seen. One popular idea is that dark matter might be made of WIMPs, weakly interacting massive particles. These particles wouldn't interact with normal matter, except through gravity and perhaps very weak nuclear forces. They would pass through you, me, and even the Earth without a trace. Other theories suggest axions, incredibly light particles that might form a sort of cosmic field. Or maybe dark matter is made of machos, massive astrophysical compact halo objects, like black holes or neutron stars that are just too faint to detect. Some scientists even think dark matter might not be particles at all. Instead, they propose it could be something entirely different, a new kind of force or interaction that we haven't yet discovered. It could even be tied to extra dimensions, hidden just beyond our perception. But here's the thing. None of these ideas have been proven. Scientists have built intricate detectors deep underground, shielded from cosmic rays. They've sent telescopes into space to search for clues. They've collided particles at nearly the speed of light in giant accelerators, looking for hints of dark matter. And yet nothing. This leaves us with one of the greatest mysteries in science. Dark matter is something we know is there. We can feel its effects, and we can see its influence on the motion of galaxies. But its true nature remains a puzzle. And so, dark matter remains a cosmic enigma, a presence we can measure but cannot see, a force that shapes the universe, yet stays just out of reach. But its effects are everywhere. Dark matter doesn't just hold galaxies together. It also helped create them. In the early universe, when everything was hot and chaotic, dark matter provided the scaffolding for ordinary matter to clump together and form stars and galaxies. Without dark matter, the universe would look very different. Perhaps it would be a vast, dark emptiness, with no stars, no planets, no life. As you listen, imagine yourself drifting through the universe, weightless. Picture dark matter as an invisible thread, woven to the cosmos, shaping everything we see. Without it, the galaxies we admire in the night sky wouldn't exist. The stars wouldn't shine, and we wouldn't be here. Dark matter is a mystery that invites humility. It reminds us that even with all our advancements, there's so much we don't know. Somewhere out there, perhaps in the quiet of a lab or the vastness of space, lies the answer. And one day, we might uncover it. But for now, we let the mystery remain. A quiet presence, holding the universe together. A reminder that the cosmos is far bigger and far stranger than we can imagine. As you drift off to sleep, think of dark matter not as something to be solved tonight, but as a gentle question posed by the universe. A question that will wait for as long as it takes us to answer. Each particle, each wave, and each silent force in the cosmos carries a story. Dark matter's story is still unfolding. And as it does, it pulls us forward toward understanding, toward discovery, and toward a deeper appreciation of the universe's endless beauty. Perhaps this is why we ponder mysteries like dark matter, not just to find answers, but to marvel at the questions themselves. So let the universe cradle you tonight, its mysteries lulling you to sleep, one gentle starry breath at a time. As you look up into the night sky, the universe seems vast, infinitely so. Stars glitter, galaxies swirl, and planets orbit distant suns. In the grand scheme of things, our tiny planet is but a speck in the cosmos. And yet, with all that space, one question lingers in the air. Where is everyone? This is the essence of the Fermi paradox, a mystery that has captivated scientists, philosophers, and dreamers for decades. The paradox arises from a simple contradiction. Given the sheer number of stars and planets in the universe, it seems almost inevitable that intelligent life would exist somewhere out there. After all, there are billions of stars in our galaxy alone, each with its own planets. The math seems to suggest that life, especially advanced civilizations, should be common in the cosmos. So why, then, haven't we detected any signs of extraterrestrial life? The vastness of the universe, combined with its age and the likelihood of countless other worlds, makes this question all the more puzzling. If intelligent civilizations are out there, why haven't we heard from them? Why hasn't anyone reached out to us? The Fermi paradox points to the quietness of the universe, an eerie silence that raises profound questions about the nature of life itself. Let's pause for a moment and think about the scale of the problem. The Milky Way galaxy alone contains hundreds of billions of stars. Many of these stars have planets in the habitable zone, the sweet spot where conditions might be right for life to exist: liquid water, stable temperatures, and the right chemical ingredients. With so many possibilities, it seems reasonable to assume that life, in some form, should have arisen elsewhere. Yet, after decades of searching, we have found no conclusive evidence of alien civilizations. What could be the reason for this silence? The possibilities are as vast as the universe itself, and scientists have proposed many theories to explain the paradox. One possibility is that civilizations may be so far apart in space and time that the chances of us crossing paths are incredibly slim. Imagine two civilizations, one in our galaxy and the other in a distant part of the universe, each unaware of the other's existence because they are separated by unimaginable distances. The vastness of space could make it impossible for civilizations to communicate or even detect one another. Another theory is that advanced civilizations may be rare, or perhaps they don't last very long. It's possible that while life may be common, intelligent life capable of developing technology might not be. And even if a civilization does arise, it could burn through its resources, destroy itself, or face some other existential threat before it has a chance to reach out into the cosmos. Perhaps civilizations reach a certain level of technological advancement only to self-destruct, a tragic cycle that prevents long-lasting contact. There's also the possibility that alien civilizations are out there, but they are deliberately avoiding us. Perhaps they are aware of our existence, but they choose not to make contact for reasons we cannot comprehend. This theory, known as the zoo hypothesis, suggests that advanced civilizations may be observing us from afar, like scientists watching a distant species in a zoo, not wanting to interfere with our natural development. If that's the case, then the silence might be intentional, a kind of cosmic restraint. Yet another intriguing possibility is that we simply don't know how to detect alien civilizations. While we've been searching for signals from distant stars, perhaps we are missing something fundamental. Advanced civilizations may be using forms of communication or technology that are beyond our current understanding. What if their methods are so advanced or so different from ours that we simply don't know how to listen? And then there's the possibility that we are indeed alone. The idea that Earth and humanity are the only intelligent life in the vast universe is a thought-provoking one. If that's the case, it raises questions about the nature of life itself. Why did it arise here and nowhere else? Is there something uniquely special about our planet? This thought, though sobering, can also be humbling, as it places an extraordinary responsibility on us to protect and cherish the life we have. The Fermi paradox is not just a question about aliens. It's a question about us. It reflects our own curiosity, our desire to explore, and our longing to know whether we are truly alone in the universe. As we search the stars, we are also searching for meaning, for connection, and for a sense of our place in the grand tapestry of existence. As you reflect on this mystery, imagine drifting in the stillness of space, surrounded by the cold, distant stars. The vastness stretches out before you, an infinite ocean of possibilities, yet so eerily quiet. Where are the other civilizations? Why are they silent? The silence of the universe is not a void. It is filled with questions, with unknowns, and with wonder. Could it be that the answer lies in the nature of life itself? Perhaps the development of intelligent life is rare, or perhaps we are in the midst of a rare moment in the universe's long history. The silence could be the result of the fragile nature of life, its brief existence, the challenges it faces, and the unpredictable forces that shape it. Let these thoughts carry you into a peaceful slumber as the mystery of the universe stretches out before you. The stars, the galaxies, and the silence all invite you to dream of what might be. Are we alone, or is there a reason for quiet? The answer may be waiting just beyond our reach, a secret hidden in the vastness of the cosmos. As you close your eyes, picture the stars twinkling, each one a potential home for life, each one a beacon in the darkness. The question of whether we are alone or whether there are others out there remains unanswered, but the search for that answer is part of the adventure of being human. It connects us to the cosmos and to each other as we share this beautiful, mysterious world. The Fermi paradox may not have an answer just yet, but the very act of pondering it brings us closer to understanding our place in the universe. Let the stillness of space wrap around you tonight as you rest, knowing that the silence of the cosmos holds endless possibilities that may one day be revealed. Imagine the universe, a vast expanse of galaxies, stars, and planets stretching out in all directions. Now, imagine something even more incredible, a force so strange and so powerful that it's causing the universe to expand faster and faster over time. This mysterious force is what scientists call dark energy. Dark energy isn't like anything we're familiar with. It doesn't shine or emit light. It doesn't interact with matter in the ways we're used to. And yet, it makes up about 68% of everything in the universe. Think about that for a moment. Nearly 7/10 of the cosmos is something we cannot see, touch, or even fully understand. The story of dark energy begins in the early 20th century with the work of Albert Einstein. When Einstein was developing his theory of general relativity, he realized something odd. According to his equations, the universe shouldn't be static. It should either be expanding or contracting. But at the time, scientists believed the universe was stable and unchanging. To make his equations fit the accepted view, Einstein added something called the cosmological constant. This constant was a kind of fudge factor, a force that counteracted gravity and kept the universe static. Years later, when astronomers discovered that the universe was actually expanding, Einstein famously called the cosmological constant his biggest blunder. But here's where the story takes a surprising turn. In the late 1990s, astronomers studying distant supernovae, exploding stars, found something shocking. The universe wasn't just expanding, its expansion was accelerating. This was completely unexpected. Gravity, the force that pulls things together, should be slowing the expansion down. Instead, something was pushing the universe apart at an ever-increasing rate. It was as if a hidden force was working against gravity, driving galaxies farther and farther away from each other. And so, the idea of dark energy was born. But what is dark energy? That's the mystery. Some scientists think it might be a property of space itself. In quantum physics, empty space isn't really empty. It's a seething, bubbling field of virtual particles popping in and out of existence. Dark energy could be tied to this vacuum energy, a kind of latent force that permeates the universe. Another possibility is that dark energy is connected to the cosmological constant Einstein proposed, but with a twist. Instead of being a mistake, the cosmological constant might be real, a built-in feature of the universe that causes space to stretch and expand. But these are just theories. Other scientists suggest that dark energy could be something entirely new, a force or field we haven't discovered yet. Some even think it might signal a breakdown in our understanding of gravity itself. Perhaps the laws of physics work differently on the largest scales of the cosmos. What's fascinating and humbling is how little we know. We can measure the effects of dark energy by observing the expansion of the universe, but its true nature remains elusive. It's like seeing ripples on a pond without knowing what's causing them. Dark energy is not just a cosmic curiosity. It has profound implications for the future of the universe. If the expansion of the universe continues to accelerate, galaxies will drift farther and farther apart. Over billions of years, the night sky could become almost completely dark, with only a few faint points of light remaining. Some scientists have even speculated about the possibility of a big rip. In this scenario, the force of dark energy becomes so strong that it tears apart galaxies, stars, and eventually even atoms themselves. While this idea is still highly speculative, it shows just how much we have yet to learn. Think about the enormity of it. Dark energy is shaping the fate of the cosmos. It's stretching the very fabric of space, altering the way the universe evolves over time. And yet, it's something we can only glimpse indirectly through its effects on distant galaxies and the cosmic microwave background, the faint afterglow of the Big Bang. As you listen, imagine yourself floating in the vastness of space. Picture dark energy as a gentle, unseen wind, pushing galaxies apart. It's not something we can feel or touch, but it's always there, quietly at work, shaping the universe in ways we are only beginning to understand. Dark energy is a reminder of how much we don't know. It invites us to marvel at the mysteries of existence, to embrace the unknown with curiosity and wonder. Somewhere out there, perhaps in the data from a distant telescope or the equations of a future scientist, lies the answer. But for now, we let the mystery remain, a force that holds the universe in its grasp, guiding its expansion and shaping its destiny. It's a question written into the cosmos itself, a question that may take generations to answer. As you drift off to sleep, let dark energy be a reminder of the beauty of the unknown. It's a story still unfolding, a puzzle with pieces scattered across the stars. And like the universe it shapes, this mystery is vast, timeless, and endlessly fascinating. Perhaps this is why we ponder these mysteries, to feel connected to something greater, to glimpse the infinite, and find comfort in the vastness of it all. So let the universe cradle you tonight, its gentle, unseen forces lulling you into a peaceful rest. Each galaxy, each star, and each ripple in the cosmos carries a secret. Dark energy's secret is one of the greatest of all. And as we journey through the stars, we carry that mystery with us, always asking, always dreaming. Let the cosmos be your guide tonight, its quiet expansion wrapping around you like a soft, cosmic embrace. Imagine the universe as it was billions of years ago, a swirling, chaotic sea of gas and light. Stars were just beginning to form, galaxies were taking shape, and the cosmos was a place of raw, untamed energy. Now, picture this. At the heart of many of these young galaxies, something incredible was happening. Behemoths, supermassive black holes, were growing millions to billions of times the mass of our sun. Supermassive black holes are some of the most fascinating and mysterious objects in the universe. They sit at the centers of most galaxies, including our own Milky Way, where one called Sagittarius A* resides. These black holes are so massive and powerful that they influence the motion of stars and even the shape of their host galaxies. But here's the mystery. How did they form? And how did they grow so quickly in the early universe? Let's start with what we know. A black hole forms when matter collapses under its own gravity, creating a region of space so dense that nothing, not even light, can escape its pull. But supermassive black holes are on a completely different scale. Some weigh as much as 10 billion suns. The question is, how could something so enormous form in a relatively short time since the universe began? One theory suggests that supermassive black holes began as smaller seed black holes formed from a collapse of massive stars. These seeds might have grown larger over time by pulling in surrounding gas, dust, and even stars. Imagine a snowball rolling down a hill, gathering more snow as it goes. That's one way to think about how these black holes could grow, by feeding on the material around them. But there's a problem with this idea. In the early universe, there wasn't enough time for seed black holes to grow into the giants we see today. Even if they were constantly devouring matter, the process would have taken much longer than the universe's age at the time when we observed the first supermassive black holes. So, how did they get so big so fast? Another possibility is that supermassive black holes form directly from collapsing gas clouds. In this scenario, instead of forming stars first, massive clouds of gas might have collapsed under their own gravity to create a black hole directly. These direct collapse black holes could have started out much larger than seed black holes, giving them a head start in their growth. There's also the idea of mergers. In the chaotic early universe, galaxies were colliding and merging all the time. When two galaxies came together, their black holes might have merged as well, combining their masses and creating an even larger black hole. This process could help explain how some supermassive black holes grew so quickly. But even with these theories, the mystery remains. Observations of the early universe show us black holes that are already billions of times the mass of the sun, existing when the universe was less than 1 billion years old. None of our current models fully explain how they formed so quickly. To solve this puzzle, scientists are turning to powerful telescopes and simulations. Telescopes like the James Webb Space Telescope are peering deep into the early universe, capturing light from the first galaxies and black holes. At the same time, supercomputers are running simulations of how black holes might form and grow under different conditions. These tools are helping us piece together the story bit by bit. As you listen, imagine yourself drifting through space, past galaxies with glowing centers. Each bright core is a reminder of the supermassive black hole lurking within, quietly shaping its galaxy. These black holes are like cosmic engines, influencing the motion of stars and the flow of gas. And yet, their origins remain a mystery, a puzzle written into the fabric of the universe. Supermassive black holes are more than just cosmic curiosities. They play a crucial role in the evolution of galaxies. When a black hole feeds on gas and dust, it emits powerful jets of energy, which can heat up the surrounding gas and even stop new stars from forming. In this way, black holes act as both creators and destroyers, shaping their galaxies in profound ways. Think about the scale of it all. A single supermassive black hole can have the mass of billions of stars. It can outshine an entire galaxy when it's actively feeding. And yet, it's a mystery how something so vast and powerful came to be. As you close your eyes, imagine the early universe as a cosmic symphony. Galaxies forming, stars being born, and black holes growing in the midst of it all. Picture the swirling gas clouds collapsing into dense points of gravity, the chaotic dance of matter that led to the creation of these cosmic giants. The formation of supermassive black holes is one of the greatest mysteries in astronomy. It's a story of growth, of power, and of the unknown forces that shape the universe we see today. And as we study these behemoths, we're reminded of how much there is left to learn. Each question brings us closer to understanding, even as it deepens our sense of wonder. Let these thoughts carry you into a peaceful rest. The cosmos is vast, its mysteries endless, and its beauty immeasurable. Supermassive black holes are just one chapter in the universe's story, a story that continues to unfold with each new discovery. Tonight, let the universe cradle you, its mysteries lulling you into a quiet slumber. Imagine the galaxies, the stars, and the black holes as part of a grand cosmic dance, one that began billions of years ago and will continue long into the future. Each piece of the puzzle is a reminder of our connection to the infinite, the timeless, and the extraordinary. As you drift off, think of the black holes at the centers of galaxies, their immense gravity shaping the cosmos around them. They are both creators and enigmas, their origins hidden in the depths of time. And yet, they are there, a silent reminder of the universe's power and mystery. Let the stars guide you tonight, their light a gentle promise of discovery and wonder. The formation of supermassive black holes may remain a mystery for now, but their story is part of the universe's endless beauty, a beauty that holds us all in its quiet embrace. Imagine a place where the very fabric of space and time bends and warps beyond comprehension, a region where gravity is so intense that nothing, not even light, can escape its grasp. This is the heart of a black hole, a region that is both awe-inspiring and deeply mysterious. At the core of every black hole lies a singularity, a point where the laws of physics, as we know them, break down. It's a place where matter is crushed to an infinite density, and space-time becomes so warped that our current understanding of the universe can no longer hold. But what exactly happens inside a black hole? And how can two of the most important theories in physics, quantum mechanics and general relativity, reconcile the mysteries of this strange region? To begin, let's take a closer look at the concept of a black hole. A black hole forms when a massive star runs out of fuel and collapses under its own gravity. The resulting object is so dense that it creates an event horizon, an invisible boundary beyond which nothing can escape. Once something crosses this boundary, it's lost to the black hole forever. The event horizon marks the point of no return, but what lies beyond it is even more perplexing. Inside the black hole, at its very core, is the singularity. The singularity is a point where the gravitational pull is infinitely strong and space-time is infinitely curved. Matter is compressed to an almost incomprehensible degree, and the usual rules of physics break down. In this region, our current understanding of space, time, and matter no longer makes sense. But there's a problem. General relativity, which is a theory that describes the behavior of large objects like stars and planets, predicts the existence of a singularity. It tells us that once you reach this point of infinite density, the laws of physics cease to be applicable. This creates a major contradiction because quantum mechanics, the theory that governs the behavior of tiny particles, operates under very different principles. In quantum mechanics, particles can exist in multiple states at once, and their behavior is governed by probabilities rather than certainties. But when we try to apply both theories to a black hole, we run into a problem. General relativity and quantum mechanics don't play well together. General relativity describes a smooth, continuous fabric of space-time, while quantum mechanics tells us that space and time at the smallest scales are far from smooth. So, what happens when these two theories meet at the singularity of a black hole? We don't know. One of the biggest mysteries surrounding black holes is how quantum mechanics can reconcile with general relativity. Scientists have been trying to develop a theory of quantum gravity, a unified framework that could describe both the vastness of space and the minute world of particles. But so far, no such theory exists. Some physicists believe that understanding the interior of black holes could unlock the secrets of quantum gravity and help us understand how these two theories might work together. As you listen, imagine yourself drifting closer to the event horizon of a black hole. The stars and galaxies around you fade into darkness. As you approach the point of no return, the pull of gravity grows stronger and stronger, warping the space around you. But even as you reach the event horizon, the true nature of what lies within remains hidden, a secret shrouded in mystery. What happens as you cross the event horizon? According to general relativity, you would be stretched and compressed in a process known as spaghettification. The difference in gravity between your head and feet will become so intense that you'd be pulled apart like spaghetti. But the real mystery lies at the singularity itself. What happens there? Is there a way for quantum mechanics to describe what occurs in this region? Some scientists propose that quantum effects might prevent the formation of a true singularity. Instead, there could be a quantum bounce at the center of a black hole where space and time are reborn, much like the Big Bang gave birth to our universe. This theory is speculative, but it offers a glimpse of a universe where quantum mechanics and general relativity might coexist. Another possibility is that black holes don't actually have a singularity at all. Instead, they could have a quantum bridge or a wormhole at their core, connecting one region of space-time to another. In this case, the interior of a black hole wouldn't be the end, but rather a doorway to another part of the universe. While this idea is still purely theoretical, it raises fascinating possibilities for what might be waiting inside. The nature of black hole interiors is not just a question of science. It's a question of the very nature of reality. By studying black holes, we're not only probing the deepest corners of the universe, but we're also challenging our understanding of space, time, and the fundamental laws of nature. As you reflect on the mystery of black holes, imagine the space around you growing darker and more distorted. The fabric of space-time stretches and twists, and you begin to feel the pull of gravity, gently guiding you toward the unknown. What lies at the center of the black hole remains a question we may never fully answer, but it invites us to ponder the limits of our knowledge and the infinite possibilities that lie beyond. The question of what truly happens inside a black hole is one of the greatest mysteries of modern physics. As you drift off to sleep, let the unknown wrap around you like a comforting embrace, knowing that the universe is full of questions that are yet to be answered. The singularity at the heart of a black hole is not just a cosmic enigma. It's a reminder that the universe is far more mysterious than we can imagine. Imagine, as you fall asleep, that you are floating in space, the black hole's event horizon just out of reach. You are surrounded by the infinite darkness of the cosmos, where time itself may behave differently. The singularity lies ahead, a secret wrapped in a cosmic riddle. And though we may never fully understand what lies within, the mystery is part of the beauty of the universe, an endless journey toward knowledge and discovery. As you lay back and look up at the night sky, the stars twinkle like distant jewels, each one a beacon of light far beyond our reach. The vastness of the universe stretches before you, so immense that it's hard to truly comprehend. And within that infinite expanse, a single question lingers. How did life begin, and how common is it? On Earth, life is a miracle, a beautiful, intricate dance of chemistry and biology that has unfolded over billions of years. From the smallest microbe to the vast diversity of plants and animals, life has taken root in nearly every corner of our planet. But as we peer into the cosmos, the question of whether life exists elsewhere remains one of the greatest mysteries of our time. Life on Earth emerged from simple molecules that, over time, evolved into the complex organisms we know today. This process, which took billions of years, is an incredible story of adaptation, survival, and growth. But while Earth is teeming with life, we have no direct evidence of life elsewhere in the universe. In fact, Earth's unique position as the only known cradle of life makes us wonder, is life rare, or is it common, waiting to be discovered in the far reaches of the cosmos? To begin, let's think about what we know. Life on Earth exists in a wide variety of forms, from the simplest bacteria to the most complex animals, all sharing certain characteristics, such as the ability to grow, reproduce, and evolve. The basic building blocks of life, such as carbon, water, and certain chemicals, are not unique to Earth. These elements are found throughout the universe, suggesting that the potential for life may be widespread. And yet, despite the abundance of the ingredients for life, we still haven't found definitive proof of life elsewhere. The mystery of life's origins lies not just in how it began on Earth, but in understanding what conditions are necessary for life to arise in the first place. What are the specific circumstances that allowed life to form on Earth? And if life emerged here, what are the chances that it could exist elsewhere, on other planets or moons, scattered across the vast stretches of space? One key factor in the search for life beyond Earth is the presence of water. On Earth, water is essential for life as we know it, providing the medium in which chemical reactions can occur. In recent years, scientists have discovered evidence of water in various forms across the universe. On Mars, in the icy moons of Jupiter and Saturn, and in distant exoplanets orbiting other stars. These discoveries have led scientists to wonder, could these places harbor life, or at least the conditions necessary for life to take root? But it's not just about water. Life as we know it also requires a stable environment, a relatively stable temperature, the right amount of sunlight, and the right chemical ingredients. For example, Earth sits in the habitable zone of our sun, the sweet spot where temperatures are just right for liquid water to exist. Too close to a star, and the heat would boil the water away. Too far, and the water would freeze. The right conditions are delicate, and it's unclear how often such conditions arise in the universe. The question of how life began is another key piece of this puzzle. Scientists believe that life emerged on Earth through a series of chemical reactions that eventually led to self-replicating molecules. This process, known as abiogenesis, is still not fully understood. We know that life on Earth evolved from simple molecules to complex forms, but how those first molecules formed and how they transitioned into living organisms remains a mystery. Was it a rare event, or could similar processes have occurred elsewhere, under the right conditions? While Earth's unique history may make it seem like life's origins are a rare occurrence, the discovery of exoplanets, planets orbiting stars outside our solar system, has opened up exciting possibilities. Thousands of these distant worlds have been discovered, and many of them lie within their star's habitable zone. Could some of these planets be home to life? Could they have conditions similar to those of early Earth, waiting for the spark that will ignite the flame of life? However, even as we search for life in distant corners of the universe, there's still much we don't know. The mystery of life's prevalence extends beyond just finding planets with water and the right conditions. We must also consider the nature of life itself. Is life as we know it the only possible form of life, or could it exist in ways we cannot even imagine? Could there be life forms that don't rely on carbon, water, or oxygen? Could life thrive in extreme environments, deep beneath the surface of planets, in the crushing pressures of distant moons, or in the intense radiation of alien stars? In some ways, this mystery brings us back to Earth. The more we learn about the diversity of life here, the more we realize how adaptable life can be. Life has been found in some of the harshest environments on our planet, from the frozen desert of Antarctica to the scalding depths of hydrothermal vents at the bottom of the ocean. If life can thrive in these extreme conditions, might it also exist in similarly harsh environments elsewhere in the cosmos? As you reflect on this question, imagine the vastness of space, stretching infinitely before you. In every direction, there are billions of stars, each with its own planets, moons, and potentially habitable worlds. Could life be out there, waiting to be discovered, just beyond the reach of our current knowledge? Could intelligent civilizations exist on distant worlds, perhaps unaware of us, just as we are unaware of them? The mystery of life's origins and prevalence is a question that transcends the boundaries of science and enters the realm of wonder. It challenges us to think about our place in the universe, to consider the possibility that we are not alone, and to explore the unknown with humility and awe. As you drift deeper into sleep, allow your thoughts to wander to the farthest reaches of the cosmos. Picture yourself floating among distant stars, passing by planets that could be home to life, worlds where conditions are just right for life to take root. In the quiet of space, the mystery of life's origins and its potential prevalence across the universe lingers like a whisper, an invitation to explore, to discover, and to imagine. Are we alone in the universe? Are there other forms of life out there, hidden in the dark expanse? The answers may one day come, but for now, the mystery remains, an ever-present question that connects us all to the cosmos, urging us to continue searching, dreaming, and wondering. Imagine a universe stretching out before you, galaxies, stars, and clusters scattered across the vastness of space. Now consider this: the cosmos, as endless and timeless as it seems, has a future, a destiny, a fate. And that fate depends on forces we are only beginning to understand. The story of the universe's future is tied to its expansion. For billions of years, the universe has been growing larger, its galaxies drifting farther apart. But this expansion raises a profound question. What happens next? Will the universe continue to expand forever? Or will it one day slow down, stop, and collapse back on itself? Could something even stranger lie ahead? To answer these questions, we must explore the forces shaping the cosmos. One of the key players is gravity, the force that pulls objects together. Imagine two galaxies. Gravity acts like an invisible tether between them, pulling them closer. But there's another force at work, a mysterious energy driving the galaxies apart, causing the universe to expand faster and faster. This is dark energy, a riddle at the heart of the universe. The interplay between gravity and dark energy will determine the ultimate fate of the cosmos. To understand possibilities, let's consider 3 scenarios. Each one offers a glimpse into a future shaped by the unknown. The first possibility is the Big Crunch. In this scenario, gravity eventually wins the cosmic tug-of-war. Over time, the expansion of the universe slows, stops, and reverses. Galaxies begin to move closer together. Stars and planets collide. The entire universe contracts, growing hotter and denser until everything collapses into a singularity, a single, infinitely small point. The Big Crunch would mark the end of the universe as we know it. But some theories suggest it could also be the beginning of something new, a cosmic rebirth where a new universe emerges from the ashes of the old. The second scenario is the opposite of the Big Crunch, the Big Freeze. Here, dark energy dominates, and the universe continues to expand forever. Galaxies drift farther and farther apart until they're so distant that their light no longer reaches us. Stars burn out, one by one, leaving behind cold, dark remnants. Over trillions of years, even black holes evaporate, and the universe becomes a vast, empty void, cold, silent, and lifeless. The Big Freeze paints a picture of an endless, quiet universe, stretching into eternity. The third possibility is the most dramatic, the Big Rip. In this scenario, dark energy doesn't just drive the expansion of the universe, it accelerates it to the point of tearing everything apart. Galaxies disintegrate. Stars and planets are ripped to pieces. Even atoms and subatomic particles are pulled apart by the relentless force of dark energy. The Big Rip will be a catastrophic end to the cosmos, leaving nothing but isolated particles scattered across an infinite expanse. Which of these futures awaits us? That's the mystery. To solve it, scientists study the properties of dark energy and the density of the universe. Is dark energy constant, or does it change over time? Is there enough matter in the universe for gravity to eventually halt the expansion? Or is dark energy so powerful that it will overcome all other forces? These are questions we don't yet have answers to. The fate of the universe is more than a scientific puzzle. It's a profound reminder of our place in the cosmos. Imagine standing on a quiet shore, looking out at an endless ocean. You can see the waves and feel the pull of the tide, but the horizon hides what lies beyond. The future of the universe is like that horizon, vast, mysterious, and unknowable. But perhaps that's what makes it so beautiful. The idea that we're part of something so much greater than ourselves. That the stars, galaxies, and forces shaping the cosmos are part of the story still unfolding. A story that stretches back to the Big Bang and forward into a future we can only dream of. As you listen, imagine yourself floating in the vastness of space, weightless and serene. Picture the galaxies around you, each one a tiny speck in the infinite expanse. Think of the forces at work, the push and pull of gravity and dark energy, the delicate balance that shapes the destiny of everything we know. The universe's fate may be uncertain, but it's a question worth pondering. Will it end in a fiery collapse, a cold eternity, or a catastrophic rip? Each possibility carries its own wonder and its own mystery. And in the end, perhaps the journey, the act of asking these questions, is as important as the answers themselves. Let these thoughts carry you into a peaceful rest. As you drift off to sleep, imagine a universe holding its secrets close, inviting you to dream of what might be. The stars, galaxies, and unseen forces are all part of this cosmic dance, one that will continue long after we're gone. The fate of the universe is a story written in the language of physics, but it's also a story of wonder and imagination. It's a reminder that we're part of something vast and timeless. And as we gaze up at the night sky, we can find comfort in the knowledge that the universe is still unfolding, still evolving, still full of surprises. Let the cosmos cradle you tonight, its mysteries lulling you into a peaceful slumber. Each galaxy, each particle, and each force in the universe is a thread in a tapestry too grand to comprehend. And yet, we are part of it, a small, precious piece of an infinite whole. As you close your eyes, think of the horizon of time stretching endlessly before you. The fate of the universe is a question that will wait patiently for us to answer. For now, let it remain a source of wonder, a gentle reminder of the beauty of the unknown. As you lie back, the vastness of space stretches before you, filled with countless stars, planets, and mysteries waiting to be unraveled. One of the most intriguing discoveries in recent years is the strange visitor that came from beyond our solar system, a mysterious object that captured the attention of astronomers and stargazers alike. This object, named Oumuamua, became famous for its unusual shape, behavior, and the many questions it raised. But what exactly is it? And could be something more than a simple comet or asteroid. The mystery of Oumuamua invites us to ponder the unknown, to stretch our imaginations, and to consider whether we are truly alone in the cosmos. In October 2017, astronomers working at the Pan-STARRS 1 telescope in Hawaii noticed an object traveling through the solar system. It was moving too fast and on too unusual a trajectory to be a part of our solar system. It was clearly an interstellar object, one that had come from another star system entirely. This object, which was later named Oumuamua, meaning scout or messenger in Hawaiian, was unlike anything astronomers had ever seen before. Its elongated, cigar-like shape, its rapid speed, and its unusual movements all stood out, prompting scientists to ask one fundamental question. What is this object, and where did it come from? At first, many scientists assumed that Oumuamua was simply a comet or asteroid, another rocky or icy body from a distant star system that happened to pass through our own. But as astronomers studied its movement, they noticed something odd. Unlike typical comets, which display a visible tail as they approach the sun, Oumuamua showed no such signs. There was no visible gas or dust streaming from it, no traditional coma that we would expect from a comet. Instead, it seemed to be tumbling through space, changing its speed in ways that could not be easily explained by gravitational forces alone. This irregular motion raised an important question. What could be causing it? Some scientists propose that Oumuamua might be an unusually shaped asteroid, one that had been flung out from its home star system millions or billions of years ago. Perhaps it was simply a fragment of a larger body that had been shattered in a cosmic collision. However, this explanation didn't fully account for its erratic speed. As Oumuamua passed through our solar system, it experienced a slight but noticeable acceleration, something that couldn't be explained by the gravitational pull of the sun or the planets alone. Comets often speed up as they approach the sun because the heat causes their icy surfaces to vaporize, creating a small thrust that pushes them forward. But Oumuamua showed no signs of such outgassing, which left scientists puzzled. This unexpected acceleration led some researchers to suggest that perhaps Oumuamua was not a natural object at all, but rather something artificial, a probe, a piece of technology, or even an alien spacecraft. The possibility that this object might be a form of alien technology was an exciting yet unsettling idea. Could this strange interstellar visitor be a signal from a distant civilization, a piece of debris sent on a journey across the galaxy by intelligent beings? The idea seemed almost too fantastical to consider, but the mystery surrounding Oumuamua made it impossible to ignore. Despite these speculations, the majority of scientists have leaned toward more conventional explanations. One such theory proposes that Oumuamua could be a fragment of a much larger object, possibly the remains of a planetesimal that was torn apart by the gravity of its parent star. The unusual acceleration, in this case, might be the result of the object's shape. Its elongated form could cause it to behave like a sail, catching the pressure of sunlight as it moved through space, providing a gentle but consistent push that altered its trajectory. This idea, known as radiation pressure, is similar to the way a solar sail works, where light itself exerts a small force on a surface. Another theory suggests that Oumuamua could be an iceberg of sorts, an object made of hydrogen ice, which could explain its strange movement. In this scenario, the hydrogen ice would sublimate when exposed to the sun, creating a gentle, steady push that would cause the object to accelerate. However, this theory still raises many questions, particularly about the object's unusual shape and the lack of visible signs of outgassing. Yet, even with these natural explanations, Oumuamua's behavior remains a mystery. Its origin is uncertain. Was it ejected from a distant star system, or did it form in the interstellar medium itself, a wandering body that traveled to the vast emptiness of space for eons before finally entering our solar system? The uncertainty surrounding its origin only deepens the mystery. Oumuamua's brief passage through our solar system sparked the curiosity of astronomers, but also raised broader questions about the nature of interstellar objects. How common are such visitors? Could there be more objects like Oumuamua in the galaxy, traveling through space unnoticed? The discovery of Oumuamua has inspired a renewed interest in the search for interstellar objects that come from outside our solar system and pass through our cosmic neighborhood. If such objects are relatively common, it might suggest that our solar system is just one stop along a vast interstellar highway where objects from distant star systems frequently pass by, perhaps carry with them stories and secrets from other corners of the galaxy. As we continue to study interstellar objects, we may one day learn more about Oumuamua's true nature. Was it a natural object like a comet or asteroid, or could it have been something much more extraordinary? Could it have been a signal, a message from distant stars, or an artifact of an alien civilization? The mystery remains unresolved, but it invites us to imagine the possibilities. As you reflect on this enigma, imagine the vastness of space, where objects like Oumuamua drift silently, traveling across the expanse of the galaxy. Picture the journeys they undertake, flung from their home systems, moving through the emptiness of space, crossing the great distances between stars, until they enter our solar system, leaving us with a glimpse into the unknown. What other mysteries might be out there, waiting to be discovered? The mystery of Oumuamua and interstellar objects invites us to look up at the stars with wonder and curiosity. It reminds us that the universe is full of surprises, that there are things beyond our comprehension, and that the search for answers is just beginning. As you drift into sleep, allow your thoughts to wander through the cosmos. Imagine the endless journeys of objects like Oumuamua, crossing through space and time, carrying with them the unknown stories of distant worlds. The mystery of Oumuamua may never be fully resolved, but the questions it raises will continue to inspire us to explore, to wonder, and to seek the unknown. As you rest and let your mind wander, the ticking of a clock may drift in the background, a steady rhythm marking the passing of moments. Time, it seems, is a constant companion in our lives, quietly moving forward, always progressing. But what exactly is time? Why does it flow the way it does? And could it ever flow backward? These questions have puzzled philosophers, scientists, and dreamers for centuries. And despite all our knowledge, time's true nature remains one of the greatest mysteries of the universe. In physics, time is often treated as a dimension, similar to the dimensions of space. Just as we can move through space, we move through time, constantly progressing from one moment to the next. In this sense, time is often thought of as an unyielding river, flowing from past to present to future, always moving forward and never backward. But why does time appear to flow this way? Why do we experience time as one-directional? And what does this mean for our understanding of reality itself? To explore the mystery of time, let's start by considering the flow of time in our everyday lives. We see the effects of time all around us. The sun rises and sets. Seasons change and we grow older. These are all manifestations of time's passage, but they don't explain the deeper nature of time itself. What causes time to move forward? Why doesn't it move backward, as we sometimes imagine in dreams or when we reflect on the past? In physics, time is often described as part of the fabric of space-time, a four-dimensional continuum that combines space and time into a single framework. According to Einstein's theory of relativity, the presence of mass and energy can bend and warp space-time, affecting the flow of time. For instance, time passes more slowly near massive objects like planets or black holes. This is known as time dilation, and it reveals that time isn't as simple as a constant, unchanging flow. Time, in this view, is influenced by the structure of the universe itself. But while relativity provides a framework for understanding how time behaves in different contexts, it doesn't answer the fundamental question: why does time seem to flow only in one direction? This directionality is what we call the arrow of time, and is one of the most puzzling aspects of our experience. Why is it that we remember the past but not the future? Why do we experience a sequence of events moving from one moment to the next without ever moving backward? One possible explanation for the arrow of time comes from the second law of thermodynamics, which states that the total entropy or disorder of a closed system will always increase over time. In simple terms, this means that systems tend to evolve from states of order to states of chaos. As time progresses, the universe becomes more disordered, and this increase in entropy provides a kind of time's arrow pointing from past to future. It's as if time is bound to this process of increasing disorder, and this gives it a direction. Yet, this explanation still leaves many questions unanswered. For instance, why did the universe start in a low entropy state? What caused the initial conditions of the Big Bang to be so ordered? And why did the universe start moving toward greater entropy? These questions speak to the deeper mystery of time's nature, and they suggest that time itself may be tied to the fundamental structure of the universe, something that we are still trying to understand. But what if time doesn't need to be one-directional at all? Could time run backward, just as easily as it runs forward? This idea has intrigued physicists and philosophers alike. In fact, some of the equations in physics, including those governing the motion of particles, are symmetric. They don't favor a particular direction of time. These time-symmetric equations suggest that, in theory, time could move in either direction, just as easily as water can flow downhill or uphill, given the right conditions. However, despite these time-symmetric equations, we never experience time running backward. Why is that? One possibility is that the increase in entropy we observe is not just a result of the laws of physics, but of the way our universe is structured. Perhaps time's forward motion is a fundamental aspect of the universe's evolution, an emergent phenomenon that arises from the way the universe functions on a large scale. In this view, time's arrow isn't a fundamental law of nature, but a consequence of the interactions between particles and the way they organize themselves over time. This raises another question. Could time's flow be an illusion? Some theories suggest that time, as we experience it, might not even be real in the way we think it is. Instead, time could be an emergent property, a byproduct of more fundamental processes. Just as temperature is an emergent property of the movement of particles, time might emerge in the way the universe evolves at the smallest scales. If this is the case, then time itself may not be a basic feature of the universe, but something that arises from the underlying laws of physics. And if time is an emergent phenomenon, what does that mean for the possibility of time running backward? In this view, time's forward flow might simply be a feature of the way the universe has evolved, shaped by the laws of thermodynamics and the expansion of space. If we could somehow reverse those underlying conditions, like reversing the expansion of the universe, perhaps time could flow in the opposite direction. But even if this were possible, it's not clear how it would affect our experience of time, or whether we could ever perceive such a reversal. The mystery of time's nature also ties into the question of its relationship with the universe's past and future. In a sense, time might be an illusion created by our perception of the unfolding events around us. Just as we experience the passage of time as a sequence of moments, it could be that the universe itself doesn't experience time in the way we do. Instead, time might be a way for us to make sense of the continuous change we observe in the world around us. As you reflect on this mystery, imagine the universe stretching out in front of you, like a river of time, flowing from one moment to the next. Could it be that time, like the river, flows only in one direction, or could it move backward, like a stream reversing its course? These questions remain unanswered, but they invite us to consider the very nature of our existence and the fabric of the cosmos. As you drift toward sleep, allow the quiet flow of time to lull you into a peaceful rest. The nature of time, with all its mysteries and paradoxes, will remain a subject of wonder as long as we continue to gaze at the stars and seek to understand the universe. And though we may never fully grasp the essence of time, the search for its true nature is a journey that connects us to the very heart of the cosmos. As you gaze into the night sky, the stars seem to stretch endlessly into the cosmos, each one a distant beacon of light. But what if, just beyond what we can see, beyond the edges of our universe, there were other realms, other realities, each with its own stars, planets, and perhaps even forms of life? This is the intriguing idea of the multiverse, the theory that our universe is just one of many, each existing parallel to the others in an infinite sea of possibilities. The concept of the multiverse is both mind-boggling and awe-inspiring. Imagine, if you will, a vast collection of universes, each with its own set of physical laws and constants. Some might be nearly identical to our own, with slight differences, while others could be entirely different, with strange laws of physics and unrecognizable forms of matter. The idea challenges our understanding of reality itself, suggesting that the universe we know is not the only one that exists. But what exactly is the multiverse, and how did it come to be a topic of scientific speculation? The term multiverse was coined to describe the idea that multiple universes could exist beyond our own. The notion isn't as new as it might seem. It has roots in ancient philosophy, but in modern times, it has been largely driven by advancements in cosmology and theoretical physics. One of the most intriguing aspects of the multiverse theory comes from the field of quantum mechanics. According to the many worlds interpretation of quantum mechanics, every time a quantum event occurs, like an atom decaying or a particle moving, it creates a new universe, one where all possible outcomes of that event are realized. In this view, every decision, every action, every possibility results in the branching reality into parallel universes. The number of these universes could be staggering, perhaps infinite, each representing a different outcome of every quantum event. Another theory comes from the field of cosmology, the concept of cosmic inflation, which explains the rapid expansion of the universe right after the Big Bang, suggests that different regions of space could have inflated at different rates, creating separate pocket universes. Each of these universes might have its own unique properties and physical laws, completely disconnected from ours. The mystery of the multiverse is profound. If there are indeed other universes, can we ever detect them? Can we interact with them in any way? Or are they forever beyond our reach, isolated in their own realms? These are questions that science has yet to answer, but they invite us to imagine the possibilities. One of the greatest challenges in studying the multiverse is that, by definition, we are limited to our own universe. Our current technology and understanding of physics are constrained by the laws that govern our reality. We cannot directly observe other universes, as they might exist beyond the observable limits of our universe. The very nature of a multiverse suggests that these universes are separate, with no way for them to interact with one another, at least not in any way that we can currently perceive. And yet, some scientists have proposed potential ways that we might be able to detect the presence of other universes. One possibility involves the study of cosmic background radiation, the faint afterglow of the Big Bang. If our universe collided with another in the past, traces of that event might be detectable in the cosmic microwave background. In this way, we could potentially observe evidence of a multiverse, even if the other universes remain out of reach. Another idea is that the multiverse could be connected to the strange and puzzling phenomena of dark energy and dark matter. If other universes exist with different physical laws, their influence might manifest in our own universe in subtle ways. Scientists are still exploring whether these mysterious forces might provide a clue to the existence of parallel universes. But even with these speculative ideas, the question remains, is there any way for us to interact with these parallel universes if they truly exist? The answer is uncertain, and many scientists believe that the multiverse, if it exists, is forever beyond our grasp. It's possible that the laws of physics simply don't allow for any kind of communication or travel between universes. If the multiverse consists of realms that are fundamentally disconnected from each other, then interaction may be an impossibility. Still, the idea of the multiverse remains tantalizing. It challenges the very notion of reality, suggesting that everything we know, every experience, every event, every outcome, could be just one thread in an infinite tapestry of possibilities. Imagine, if you will, the sheer vastness of this idea, an endless expanse of universes, each with its own unique story to tell. As you contemplate this mystery, picture yourself floating in a quiet expanse of space, surrounded by countless galaxies. Each one of those galaxies might be home to a universe that exists just beyond your reach, invisible to you, but possibly shaped by the same forces that govern your own. Could there be other versions of you in these other universes, living out different lives, making different choices, experiencing different outcomes? The possibilities are infinite, and the mind can scarcely comprehend them all. The mystery of the multiverse is not just a question of science. It is a question of existence itself. It asks us to imagine a reality that is far bigger, far more complex, and far more mysterious than we ever thought possible. It challenges us to expand our horizons, to think beyond the confines of our own universe, and to wonder whether there is more to reality than meets the eye. As you let your thoughts drift deeper, allow the mystery of the multiverse to settle into your mind. The idea that there are other universes, other possibilities, is a beautiful thought, a reminder that the universe is vast and full of wonder, and that we are only beginning to scratch the surface of what lies beyond our own reality. Let these thoughts carry you into a peaceful sleep as you ponder the infinite potential of the multiverse. In the stillness of the night, the idea of parallel universes may seem far away, but they are part of the great mystery of existence, a mystery that continues to inspire us to reach for the stars and seek answers to the deepest questions of life. As you drift off, imagine the vast expanse of the multiverse stretching out before you, with infinite possibilities waiting to be discovered. Each universe, a reflection of a different reality, is part of the grand cosmic dance, an endless journey of exploration and discovery.